Claustrophobia is a real thing that affects many people. However, the whole universe may be in for a rude shock as scientists have made new discoveries that suggest the universe is collapsing on itself. Is it time to hit the panic button? Find out as we dive into the intriguing theories that the universe is collapsing and not expanding. The universe is a vast and mysterious place that's fascinated humans for centuries. How did it begin and how will it end? These are some of the questions that cosmologists, scientists who study the origin and evolution of the universe, try to answer using observations and theories. One of the most widely accepted theories about the beginning of the universe is the Big Bang Theory. According to this theory, about 13.8 billion years ago, all matter and energy in the universe was concentrated in a tiny point called a singularity. This singularity was extremely hot and dense, and it exploded in a colossal burst of expansion. This event, known as the Big Bang, created space and time and filled them with radiation and elementary particles. As the universe cooled down, these particles formed atoms, molecules, stars, galaxies, and other structures that we see today. The Big Bang Theory is supported by several lines of evidence, such as the cosmic microwave background (CMB), which is the faint radiation left over from the early stages of the universe, the abundance of light elements such as hydrogen and helium, which were produced in the first few minutes after the Big Bang, and the redshift of distant galaxies, which indicates that they're moving away from us due to the expansion of space. However, the Big Bang Theory does not tell us everything about the universe. It does not explain what caused the singularity to explode, what happened before the Big Bang, or what will happen in the future. For these questions, cosmologists have proposed various scenarios based on different assumptions and models. One of these scenarios is the Big Crunch theory. This theory suggests that the expansion of the universe will eventually stop and reverse due to the gravitational attraction of matter. In other words, the universe will start to contract and collapse back into a singularity, undoing the Big Bang and ending everything that exists. The Big Crunch theory is based on the idea that the fate of the universe depends on its density and its rate of expansion. The density of the universe is the ratio of its mass to its volume, while its rate of expansion is measured by a parameter called the Hubble constant. These two factors determine whether the universe is open, closed, or flat. An open universe has a low density and a high rate of expansion. In this case, gravity is not strong enough to overcome the outward push of dark energy, a mysterious force that causes space to accelerate its expansion. An open universe will expand forever, becoming colder and emptier over time. A closed universe has a high density and a low rate of expansion. In this case, gravity is stronger than dark energy and will eventually slow down and reverse the expansion. A closed universe will end in a big crunch. A flat universe has a critical density and a balanced rate of expansion. In this case, gravity and dark energy are in equilibrium and cancel each other out. A flat universe will expand at a constant rate forever. Now, the shape of the universe can be determined by measuring its curvature using observations of distant objects such as galaxies or supernovae. Current measurements suggest the universe is flat or very close to flat. However, this does not rule out the possibility of a big crunch, as there may be uncertainties or errors in these measurements. Another factor that could affect the rate of the universe is dark matter. Dark matter is a type of matter that does not interact with light or ordinary matter, but has gravity. Dark matter makes up about 27% of the mass-energy content of the universe, while ordinary matter makes up only about 5%. The rest is dark energy. The presence of dark matter could increase the density of the universe and make it more likely to collapse. But if the Big Crunch theory is true, what would happen to the universe as it contracts? According to some calculations, it would take about 100 billion years for the contraction to become noticeable. As galaxies get closer together, they would collide and merge into larger structures. Stars would also collide and ignite into supernovae or form black holes. The temperature and pressure of matter would increase dramatically as space shrinks. Eventually, all matter would be compressed into a single point with infinite density and temperature, similar to the initial singularity before the Big Bang. At this point, known as the final singularity or omega point, all physical laws would break down and time would cease to exist. The universe would end in a fiery cataclysm. However, some cosmologists have speculated that this might not be the end of everything. They have suggested that the Big Crunch could be followed by a new Big Bang, creating a new universe with different properties and laws. This could imply that the universe is cyclical, going through infinite cycles of expansion and contraction. This idea is known as the Big Bounce theory. The Big Crunch theory is one of the possible scenarios for the ultimate fate of the universe. It proposes that the universe will eventually stop expanding and collapse into a singularity, ending everything that exists. However, this theory is not widely accepted by cosmologists, as most observations indicate that the universe is expanding at an accelerating rate due to dark energy. The Big Crunch theory also faces several theoretical and empirical problems, such as the initial singularity and the entropy issue. Therefore, it is more likely that the universe will end in a different way, such as heat death or a big rip. The Big Rip theory suggests the expansion of the universe will continue at an accelerating rate due to dark energy, a mysterious force that causes space to expand faster and faster. In other words, the universe will rip itself apart by stretching everything in existence, from galaxies to atoms and even space-time itself, until distances between particles become infinite. The Big Rip theory, like the Big Crunch theory, is based on the idea that the fate of the universe depends on its density and its rate of expansion. Now, current measurements suggest the universe, as mentioned before, is flat or very close to flat. However, this does not rule out the possibility of a Big Rip. The key factor that could cause a Big Rip is the equation of state parameter W, which describes how dark energy behaves. It is defined as the ratio between dark energy pressure and dark energy density. If W equals -1, then dark energy behaves like a cosmological constant, which means that its density remains constant as space expands. In this case, dark energy will not affect bound structures such as galaxies or stars. If W is greater than -1 but smaller than 0, then dark energy behaves like a quintessence, which means that its density decreases as space expands. In this case, dark energy will still not affect bound structures but will cause them to drift apart over time. If W is less than -1, then dark energy behaves like phantom energy, which means that its density increases as space expands. In this case, dark energy will overcome all forces that hold bound structures together and rip them apart. The value of W is not well known, but most observations suggest that it's close to -1. However, there are some uncertainties and errors in these measurements that could allow for W being less than -1. If W is less than -1 and phantom energy dominates the universe, then according to some calculations by Robert Caldwell and his colleagues who proposed the Big Rip theory in 2003, there will be a finite time in the future when the Hubble constant will become infinite and the universe will end in a singularity. The time from the present to the Big Rip depends on the value of W and the current density of dark energy. For example, if W equals -1.5 and the current density of dark energy is 70% of the total density of the universe, then the Big Rip will happen in about 22 billion years. As the Big Rip approaches, the universe will undergo dramatic changes. The expansion of space will accelerate and the size of the observable universe and the cosmological event horizon will shrink. The event horizon is the distance beyond which light cannot reach us due to the expansion of space. As the event horizon shrinks, we will lose contact with the distant galaxies and stars, and eventually all bound structures will be torn apart by dark energy. First, galaxies will be ripped apart as their stars fly away from each other. Then solar systems will be ripped apart as planets are flung away from their stars. Then stars and planets will be ripped apart as their atoms are stretched and broken. Finally, even atoms and subatomic particles will be ripped apart as space-time itself becomes infinitely stretched. At this point, known as the final singularity or omega point, all physical laws will break down and time will cease to exist. The universe will end in a catastrophic rupture. However, some cosmologists have challenged or criticized the Big Rip theory. For one thing, it's not clear how phantom energy can exist or how it can violate the dominant energy condition, which states that energy density should always be positive or zero. And for another thing, there is no direct evidence or observation to support the existence of phantom energy or W being less than -1. Moreover, some alternative models have been proposed to avoid or modify the Big Rip scenario. For example, some models suggest that dark energy could change its behavior over time and switch from phantom energy to quintessence or cosmological constant before the Big Rip happens. Other models suggest that dark energy could interact with the dark matter or ordinary matter and reduce its effect on bound structures. And still other models suggest that quantum effects could prevent space-time from becoming infinitely stretched and create a bounce or a transition to another phase of the universe. Now, the Big Bounce theory mentioned earlier is a popular cosmological concept that investigates the origins and potential fate of our cosmos. According to this hypothesis, our world is merely one of many unending cycles of expansion and contraction. It implies a universe that is constantly collapsing on itself only to bounce back and produce a new universe, avoiding the idea of a big crunch or an ultimate singularity. Now, the Big Bounce theory runs counter to the generally held Big Bang concept, which holds that our universe arose from a singularity roughly 13.8 billion years ago and has been expanding ever since. This model predicts a future of continuous growth culminating in a heat-death scenario in which the universe reaches maximum entropy. According to the Big Bounce concept, though, the cosmos does not begin with a singularity, but rather with a collapse of a prior universe. According to this idea, when gravity is exerted at extreme levels, it can function as a repulsive force rather than an attractive one. This is when quantum effects enter the picture. According to the quantum theory of gravity, at these extreme conditions, the fabric of space-time itself may exert a form of pressure, forcing a collapsing universe to bounce back out, resulting in an expansion phase, thus the Big Bounce. A collapsing universe's physics is extremely complex. To comprehend them, we must combine general relativity, which describes gravity on a vast scale, with quantum mechanics, which governs on a microscopic scale. The union of these two opposing ideas yields quantum gravity, a theoretical framework required for explaining phenomena such as black holes and the early cosmos. According to the Big Bounce hypothesis, when the universe shrinks, it reaches a point of maximum density, at which quantum gravitational effects become significant. Gravity switches roles and behaves repulsively when matter, space, and time collide. This causes a bounce, resulting in another period of expansion and the genesis of a new universe. Now, the idea of a cyclic cosmos is not novel in cosmology. The mathematical account of how a collapsing universe can recover, on the other hand, has proven to be a serious issue. However, a bouncing universe is supported by some versions of string theory, loop quantum cosmology, and other unifying theories, lending validity to this idea. Nevertheless, the evidence for the Big Bounce theory is currently circumstantial, based mostly on the Big Bang model's limitations and the logical implications of quantum gravity. However, it has been proposed that the cosmic microwave background radiation may contain signs of a former universe that existed before the bounce. And despite the fact that the Big Bounce theory has yet to be proven, its implications are substantial. It calls into question our concept of the nature of time, the origins of the universe, and its ultimate fate. Its most profound implication, however, may be that it removes the cosmos from the realm of the finite. The universe, according to the Big Bounce idea, is everlasting, cycling through infinite phases of expansion and contraction. This viewpoint adds new dimensions to cosmological philosophies and astrophysical models, as well as fresh areas for future investigation. The Big Bounce idea is a fascinating new frontier in cosmology. It proposes a universe model that defies traditional thinking regarding beginnings and endings, instead proposing an infinitely cycling cosmos. And as scientists wrestle with these concepts, we may anticipate our understanding of the world to change and expand, much like the universe itself. The theory of the cyclic universe is a model of cosmic evolution according to which the universe undergoes endless cycles of expansion and cooling, each beginning with a Big Bang and ending with a big crunch. One version of this theory is the brain cosmology model, which proposes that the universe is created by the collision of two parallel planes or brains in a higher dimensional space. Paul Steinhardt and Neil Turok suggested a novel cycle model, the cyclic model of the universe. A membrane or brain in string theory is an object that exists in a specific number of dimensions. Our observable three spatial dimensions, according to Steinhardt and Turok, correspond to one of these brains. Two parallel three-dimensional brains could exist separated by an extra hidden dimension. These brains, imagine them as metal sheets, may move along this extra dimension and clash, resulting in a Big Bang and, eventually, our universe. When they hit, the standard Big Bang scenario is followed. Hot matter and radiation are formed, there is rapid inflation, then cooling, and the formation of structures such as galaxies, stars, and planets. Steinhardt and Turok, on the other hand, claim that there is always a force between these two parallel brains, which he refers to as an interbrain force. This force is what brings the brains together, causing them to smash again, resulting in another Big Bang. Eventually, the universe reaches a maximum size and begins to contract due to gravity, leading to a big crunch and another collision. This process repeats infinitely over time. The theory of the cyclic universe supports the idea that the universe will collapse on itself because it assumes that the expansion of the universe is not eternal but rather limited by a certain amount of energy or matter. When this limit is reached, the universe reverses its direction and falls back into itself, creating a singularity that explodes again in a new cycle. Some versions of this theory also suggest that the collapse of the universe is triggered by the evaporation of black holes or the decay of the vacuum state. Some of the proposed evidence for the cyclic universe includes rings of uniform temperature in the cosmic microwave background, which could be the signature of gravitational waves emitted by colliding black holes in the previous cycle. Unexpected hotspots in the CMB, which could be the result of black holes evaporating before the Big Bang and leaving behind traces of radiation. The small value of the cosmological constant, which is the repulsive force that drives the accelerated expansion of the universe. According to the cyclic model, this value decreases over time during each cycle, explaining why it is so much smaller than predicted by the standard Big Bang model. However, these pieces of evidence are not definitive and face many challenges and criticisms from other cosmologists. Some of the issues include the lack of direct observation or experimental verification of the processes involved in the cyclic model, such as brain collisions, black hole evaporation, or mass loss. The conflict with the second law of thermodynamics, which states that entropy or disorder in a closed system will always increase over time. This implies that each cycle would be more chaotic and less structured than the previous one, contradicting the observed uniformity and regularity of the universe. The difficulty of explaining how the initial conditions and physical laws of each cycle are set or preserved across different cycles, especially if there is a singularity or a quantum fluctuation involved in each transition. Now, the cyclic universe theory has some advantages and disadvantages compared to the standard Big Bang model. Some of the advantages are the cyclic model can explain the cosmological constant, but the Big Bang model cannot. The constant's value is responsible for the universe's accelerated expansion. It explains why the cosmos is expanding so swiftly. However, observations of the rate of acceleration indicate that the cosmological constant has a very tiny value. In fact, the figure is 120 orders of magnitude lower than what the mainstream Big Bang hypothesis predicts. One of the most serious issues in cosmology today is the gap between observation and theory. Another advantage to the cyclic universe theory is that it can avoid the initial singularity problem, which is the idea that the universe started from a point of infinite density and temperature, where the laws of physics break down. According to the cyclic model, there is no initial singularity, but rather a series of transitions between different phases of the universe. And the cyclic model can also provide a complete history of the universe without invoking any unknown physics or arbitrary initial conditions. According to the cyclic model, the cycles can continue indefinitely into the past and the future, and the solution is an attractor, meaning that it's stable and robust against perturbations. And then there is also the conformal cyclic cosmology (CCC) theory, which is a cosmological model proposed by theoretical physicist Roger Penrose that suggests the universe has no beginning or end, but rather iterates through infinite cycles of expansion and cooling. In this theory, though, each cycle or eon ends when the universe becomes dominated by photons and loses its mass and structure, making it indistinguishable from the initial state of the next cycle. Penrose claims that there are traces of the previous eons in the cosmic microwave background radiation, such as the patterns left by evaporating black holes or colliding supermassive black holes. The CCC theory is based on the idea of conformal geometry, which is a type of geometry that preserves angles but not lengths or distances. Penrose argues that in the very early and very late stages of each eon, when the universe is filled with radiation and has no mass, the physical laws are invariant under conformal transformations. This means that these stages can be smoothly connected across eons without any singularity or discontinuity. Penrose also argues that fermions, which are particles with half-integer spin such as electrons and protons, are confined to a given eon and cannot cross the boundary between eons. This provides a convenient solution to the black hole information paradox, which is a problem that arises from the apparent loss of information when matter falls into a black hole. The CCC theory challenges the standard Big Bang model and the inflationary paradigm, which have some shortcomings and unresolved problems. For example, the Big Bang model implies a singularity at the origin of the universe, which is a point where the physical laws break down. And the inflationary paradigm implies a period of exponential expansion in the early universe, which is supposed to solve some puzzles such as the flatness problem and the horizon problem, but it also introduces new issues such as the multiverse problem and the graceful exit problem. The CCC theory avoids these problems by proposing a cyclical structure instead of a singular origin, and by explaining the observed features of the universe without invoking inflation. The CCC theory is not widely accepted by cosmologists as it has not been confirmed by observational evidence, and it faces some theoretical difficulties. For example, it requires that all massive particles eventually decay or lose their mass, which has not been observed. It also predicts that there are observable traces of the previous eons in the cosmic microwave background radiation, such as the patterns left by evaporating black holes or colliding supermassive black holes, but these have not been convincingly detected. Moreover, it does not explain what causes the transition from one eon to another or what determines the physical constants and initial conditions of each eon. The CC theory is an interesting and provocative alternative to the standard cosmological model, but it remains a speculative and controversial idea that needs more empirical and theoretical support. It does offer a new perspective on the nature of time, the evolution of cosmic structure, and the fate of the universe, but it also poses many questions and challenges for our understanding of physics and cosmology. But it does provide a convenient solution to the black hole information paradox by suggesting that fermions are irreversibly converted into radiation during black hole evaporation to preserve the smoothness of the boundary between eons.